Hello friends, I hope it is a beautiful morning wherever you are, and IBM is my name. I welcome you to yet another episode of Learning Physics with me, and I want us to take gravitation further. This is lesson number 3. Don't forget, we are dealing with the physics 9702, 9702, and this is specifically paper 4, Cambridge Physics 9702, Advanced Structured Questions. So make sure you are in the right curriculum. So the last time we were here, I think we were looking at gravitational field strength G, where we established that G is equal to capital G M over R squared, and we saw how G varies inside and outside the Earth's surface. So I want us to continue with our examples. So I think we had done example number 1. I don't want us to go back to that example. We had done example number 2, we had done example number 3, and we had done example number 4, so I don't want to go back to that. But just to remind ourselves, I think for example number 4, we calculated that the gravitational field strength G was equal to approximately 1.1 times 10 power negative 22 newtons per kilogram as the gravitational field strength due to U at a distance equal to the radius of the Earth. That is, this will be the force that you exert on the unit mass of the Earth if the field was created by you. So that's what we obtained in question number 4. Then in question number 5, in view of your answers to the two questions above, your field strength at a distance of 6,400 kilometers from you is much weaker than the Earth's field strength at a distance of 6,400 kilometers. So we saw that the Earth's field strength, this was in question number 3. The gravitational field strength caused by the Earth on you, if you are at a distance that is just on the surface, you are at a distance of 6,400 kilometers from the center, was 9.8 newtons per kilogram. And we have seen in number 4, example 4, that the gravitational field strength caused by the person or due to you on the Earth, that is on the center of the Earth, if you are standing at a distance which is equal to the radius, was actually 1.1 times 10 power negative 22 newtons per kilogram. This is the value of gravitational field strength you cause on the Earth. This is the value that it causes on you. So the question is, in view of your answers to the two questions, can you explain why is then that you and the Earth exert the same size of force on each other? You are seeing that the gravitational field strength caused by you on the Earth is this. And the gravitational field strength, this is caused on the Earth by the Earth on you. The gravitational field strength caused by you on the Earth is this. Then can you explain why is then that you and the Earth exert the same size of force on each other? Remember we said when you are standing on the Earth's surface, you're exerting a force on the Earth's surface due to your weight, or the Earth is pulling you towards its center, but you are also pulling away from the center. Let's try to see the force exerted. So let's see the force we exert on the Earth's surface due to the Earth's gravity. That is going to be equal to, this will be the weight W, which will be equal to M times G. So we are seeing the force you exert on the Earth's surface, which is your weight. This will be now your weight. We used, I think, the previous example, we used 70 kilograms. That is your mass, times G, which is 9.81. Pressing the calculator, 70 times 9.81. This is giving us approximately 6.7. This, which is approximately at one significant figure, I'll take one significant figure, is approximately 700 newtons. That is the force we exert on the Earth's surface due to the Earth's gravity. Let us also see the force which the Earth exerts on us due to our own gravity on it. So this will be equal to the mass of the Earth, which is 6.0 times 10 power 24 times the gravitational field strength caused by us, which is 1.1 times 10 power negative 22. Pressing the calculator. So this is giving me 660 newtons, which is approximately 700 newtons. So you notice that the two forces are equal, but these are going to be opposite. So because the actual force acting on an object at a point in a field is actually the product of the field strength and the object's mass, the product is the same in both situations. The product of the mass and the field strength in question 4 and in question 3 are actually the same. Therefore, in both cases, this product we are seeing is approximately 700 newtons, and this can equally be viewed as the student's weight on the Earth's, or the person's weight on the Earth's gravitational field, or the Earth's weight in the student's or in the person's gravitational field. So this is the person's weight in the Earth's gravitational field, and this is the Earth's weight. Actually, this is the person's weight in the Earth's gravitational field, and this is the Earth's weight in the person's gravitational field. This one is in the Earth's gravitational field, this is in the person's or the student's gravitational field. Okay, so I have tried to explain this. So we are saying the actual force acting on an object is equal to the product of the field strength and the mass placed there, which is the same as this. The product of the mass which is placed there and the field strength. And we have seen the product in the case of the mass and the Earth's gravitational field is that the product in the case of the mass of the Earth and the person's gravitational field is that these two values are approximately the same to one significant figure. Okay, next is example number 6. Assume the Earth has an average density rho. Write the expression G equals to capital G m over r squared to include the density rho. The volume of a sphere is given by 4 over 3 pi r cubed. Now assume that the moon has the same average density as the Earth. On the surface of the moon, the gravitational field strength is about 1.6 newtons per kilogram, and use this to estimate the radius of the moon. So let's begin with the first part of the equation. We want to include rho in this expression here. So in our solution, the gravitational field strength is capital Gm over r squared. And we know that the mass of the mass is given by density times volume. The volume has been given, so this will be density times 4 over 3 pi r cubed. And therefore, when we substitute, we are going to substitute for the mass. So G is going to be equal to capital G times density 4 pi r cubed divided by 3 times r squared. So simply, we simplify this. When we simplify this, we come up with the G being equal to, this will be 4 over 3 capital G times density times pi r cubed cancels with r squared, will remain with 1r. So this is the expression that we want to obtain. Okay, so the g can be expressed in terms of that. So it means for bodies of the same density, if the density is not changing, the field strength at their surface is directly proportional to their radius. If the density is not changing, then we are saying that the field strength is directly proportional to the radius. If you have two planets such as Jupiter, Mars and the Earth, if they were to have the same density, then their gravitational field strength will be directly proportional to their radii, because the radius determines the size, and gravitational field strength also depends on the size. Okay, so on the surface of the moon, the gravitational field strength is 1.6. Use this to estimate the radius of the moon. Okay, so if on the surface of the moon, the gravitational field strength is 1.4, I think I need two equations. I will need two equations. So I am going to simply use G on the Earth's surface is capital G times the mass of the Earth, divided by R, radius of the Earth squared. And also G on the moon's surface is going to be capital G times the mass of the moon, divided by R, radius of the moon squared. So we want to estimate the radius of the moon. We would like to estimate the radius of the moon. So why can't I use just radii? Okay, let me just use the expression given here. This will make my life easier other than bringing in a lot of new constants. So we have already established that gravitational field strength is equal to 4 over 3 pi times density times G times R. I'll just use this expression straight away. Although this assumption is wrong, you can't assume that the moon has the same average density as the Earth. So let me just substitute. Considering the Earth, G is 9.81 equals to 4 over 3 pi times the density times capital G times the radius of the Earth, which is 6.4 times 10 power 6. Then for the moon, G on the moon is 1.6. This is going to be 4 over 3 pi. The average density is the same times G times the radius of the moon. So I'm dividing the two equations. All these cancel out. So I'm having 1.6 divided by 9.81 being equal to R in the numerator over 6.4 times 10 power 6. All these have cancelled when I divide. So R is going to be 1.6 over 9.81 times 6.4 times 10 power 6. Pressing my calculator, 1.6 divided by 9.81 times 6.4 exponent 6. So R will be 1.0 times 10 power 6. So R will be 1.0 times 10 power 6 meters as the radius of the moon. know that the assumption made here is really not acceptable, but according to the question, that assumption has been given. Now, when you look at this, for those of you who can think about this expression very well, you might be getting an impression as if G is directly proportional to R, yet we have already said that as we move away from the Earth's surface, G decreases as the inverse square. But when you look at G equals 4 over 3 pi rho G R, since density is constant, G is a constant, 4 pi over 3 is a constant, you get an impression as if G is directly proportional to R. Does it violate the inverse square? Or does it violate the inverse square law? Not really. Although it is appearing as if G is directly proportional to R, the inverse square law is not really violated. For this particular case, yes, it's true, G is directly proportional to R. But why is it like this? It's only because we are dealing with the field strength on the surface of a planet or on the surface of an object. And it means as the radius of the object we are dealing with increases, as the radius of the object we are dealing with increases, it means the volume has increased. And if the volume has increased, it also means the mass has increased, even though the density may not change, because after all, the density is equal to mass over volume, meaning that mass is directly proportional to volume. If R increases, that means the radius of the object we are dealing with has increased. It means the mass has increased, the density has not changed. So it's only because we are dealing with the field strength on the surface of a planet. We are not moving out from the surface, we are still on the surface. So as the radius of the planet increases, its mass also increases with the radius. Its mass also increases with the radius. And if we look at the expression G is equal to capital Gm over R squared, then it makes sense because as the radius increases, the mass also increases. As the radius increases, the mass also increases. So it therefore implies that the component R squared is actually going to be dependent on the mass in the numerator. The component R squared will actually be affected because if R increases, that is the radius of the sphere increases, it means the mass has increased. And if the mass has been increased, then the radius as the radius of the planet increases, its mass increases with the radius. That is going to be for a constant density. After all, we are seeing that the mass is directly proportional to the volume. But remember, of course, the volume will be dependent on R cubed. Since the volume is equal to 4 over 3 pi R cubed, it means the mass will actually be directly proportional to R cubed. Because as the radius increases, it means the volume is increasing. That means the mass is also going to be increasing because for a constant density, the mass is directly proportional to volume. Therefore, the mass is directly proportional to R cubed. So if we look at the expression G is equal to capital Gm over R squared, then this quantity R cubed here, which is in the volume, is actually depending on the mass, or it is determining the mass. In the numerator, this denominator here, which is R squared, will be dominant or will dominate. The quantity R cubed will dominate this R squared, which is in the denominator, because volume is directly proportional to mass. and volume is r cubed. So mass is directly proportional to r cubed. So it means the r cubed in the numerator, which is affecting the mass, will dominate the r squared, which is in the denominator. That's why we are getting an impression as if G is directly proportional to R. On overall, we are getting an impression that G is directly proportional to R. So if I have a larger object and a smaller object, it means G on this surface here and G on this surface here will not be the same because the value of R is actually bigger, meaning that the mass of this and the volume are relatively bigger for the same density. G on this part here will be greater than G on this surface here. Therefore, we have not actually violated the inverse square law. That is for only most students with high levels of understanding, but that is just an extension of that. It's not very, very necessary at this level. Number 7. In fact, the radius of the moon is 1.7 times 10 power 6 meters. In view of your answer to question 6, what does this suggest about the average density of the moon compared with that of the Earth? The actual radius of the moon is approximately 1.7 times 10 power 6 meters. I mean, the actual radius of the moon is approximately 1.7 times 10 power 6 meters. But we have calculated the radius to be approximately 1.0 times 10 power 6 meters. How does the density of the moon compare with the density of the Earth? Or what does this value suggest about the average density of the moon compared with that of the Earth? Of course, we can still guess that if the density, if G is equal to 4 over 3 rho pi gr, that is G is directly proportional to the density if they have the same radius, and G is directly proportional to the radius. Since the radius of the moon is 1.7 times 10 power 6 and the radius of the earth is 6.4 times 10 power 6, then we have G on the moon, we also have G on the earth's surface. So you must have observed that if the radius is bigger, then we expect the density to be smaller than we have assumed. If the radius is bigger, we expect the density to be smaller than we have assumed. What does this imply? The average density of the moon must be less than that of the earth because the moon has a smaller radius than the earth. You notice that the density is G is directly proportional to density and also directly proportional to R. And we are saying if R is bigger, then we expect the radius to be smaller. If the radius is bigger, then we expect the density to be smaller. We know that the radius of the moon is they have told us is 1.7. Okay, so let's just do this mathematically. I think mathematically it will be very easy. So we are going to substitute in this expression to see how the densities of the moon and the earth actually compare with each other using this expression here. When I consider the earth in this expression, I have 9.81 divided by, for the moon is 1.6, is equal to 4 over 3 will be the same, pi will be the same, g will be the same. It is only rho which is changing. For the earth, I will call it density of the earth divided by density of the moon times r will be different, r of the earth over r of the moon. Let's try to substitute quantities that we already know. I'm making density of the moon the subject. So maybe let me first substitute. So I have 9.81 over 1.6 being equal to density of the Earth divided by the density of the moon times the radius of the Earth 6.4 times 10 power 6 divided by 1.7 times 10 power 6. That's what we're actually getting. So when we make this the subject, because we are interested in the density of the moon, so the density of the moon, rho of the moon, will be equal to, now I take the whole of this the other side. I get the okay, I've taken density of the moon to the left. So when I take this to the right, I get the reciprocal. So this is going to be density of the Earth times 1.6 over 9.81, then times 6.4 times 10 power 6 over 1.7 times 10 power 6. So when I simplify this, 10 power 6 has cancelled. So this is approximately the same as, this is because 1.6 is close to 1.7. Okay, let me press my calculator. 1.6 times 1 times 6.4 divided by 9.81. This is approximately the same as 1 over 1.7. So it means, or it shows that the density of the moon will be approximately 1 over 1.7 times the density of the Earth. Because we notice that actually this is 1.7 times the value that we obtained earlier on. So it means the density of the moon will be 1 over 1.7 times the density of the Earth. So the average density of the moon is less than that of the Earth, because the moon's radius the moon's radius is actually 1.7 times the value that the value that we have obtained. That means its density will actually be 1 over 1.7 times the value of the density of the Earth. As simple as that. Okay, self-check. Self-check. You may refer to this table where necessary because you may need some of these values. The Earth has the mass of that, the Moon has this mass, Sun has that mass. These are in kilograms. The radius, Earth is 6400, Moon is 1740, the Sun is 700. These are in kilometers. And the distances from the Earth, the distances from the Earth, you can't measure the distance of the Earth from the Earth. That doesn't make sense. For the Moon has this distance from the Earth, and the Sun has this distance from the Earth. So you will always refer to these values for the self-check. Question number 1, which is number 8, they are continuations of the examples actually. The mass of Jupiter is 1.9 times 10 power 27. Its radius is 7.1 times 10 power 7. Calculate the gravitational field strength at the surface of Jupiter. So you are calculating small g. You are verifying if that answer is correct. Number 9. Mount Everest is approximately 9.0 kilometers high. Calculate how much less a mountaineer of mass 100 kilograms, including backpack, would weigh at sea level. Would this difference be measurable with the bathroom scales? When somebody talks about bathroom scales, is referring to the normal scales. Can they measure the difference? If you get a difference in the weight which is greater than, which is 1 and above, of course that is measurable. If it is very, very small, then such values, we say they are not measurable with bathroom scales or normal scales. So All you need is you are going to find G on top of a mountain, G on the mountain, and use it to find the weight on the mountain. Then G on the surface at sea level is approximately 9.81. Then find the weight at sea level. Then find the difference. If the difference is greater than 1 Newton or 1 and above, then it is measurable at bathroom level. But I want you to note that as you go up on top of the mountain, other factors such as dehydration would also be more significant. When you go up, dehydration is very significant. This could also affect your weight. So find G on top of a mountain. Of course, on top of mountain, it means you add the radius of the earth to this value here to get the distance from the center of the earth. That will help you to find G on top of a mountain. Then use it to calculate the weight, subtract it from the weight, or subtract the weight or from the weight on the earth's surface where G is 9.81, and the difference is what we need here. And I have said if the difference is greater than 1 or 1 and above, then it is measurable with normal scales. Now, number 10, calculate the gravitational field strength close to the surface of the moon, close to the surface of the sun. Suggest how your answers above help to explain why the moon has only a thin atmosphere. Sometimes we say the moon has no atmosphere. For the explanation, I'll try to talk about it. So the gravitational field strength at the moon is this. Compare it with the gravitational field strength at the sun. The gravitational field strength is very weak on the moon, so the gas molecules will easily escape. The gas molecules will have enough energy to escape from the moon. Remember, it is these gas molecules which create the atmosphere. But now we are seeing that the gravitational field strength at the moon is very weak. So the gas molecules have enough energy to escape from the moon, leaving almost no atmosphere or leaving a thin atmosphere. Whereas the sun, you will calculate and verify that its gravitational field strength is 270 newtons per kilogram. This is way high. It is a very high field strength. This therefore pulls most of the gases close to the surface of the moon. Therefore, the moon has a dense atmosphere. The gravitational field strength around the moon, the sun, is very high. This would pull most of the gas molecules towards the sun. This makes the sun to have a very dense atmosphere. So the moon is said to have a thin or no atmosphere because of a very weak gravitational field strength. Okay. Then number 12, number 11, calculate the Earth's gravitational field strength at a position of the moon. Here you will need to use the radius of the moon, the distance from the Earth's center to the moon. Calculate the force the Earth exerts on the moon. So here you need the distance between the Earth and the moon and their masses. Hence, determine the moon's acceleration towards the Earth. That is, you want the acceleration due to gravity at the position of the moon. Then next, Jupiter's mass is 320 times that of the Earth, and its radius is 11.2 times that of the Earth. The Earth's surface gravitational field strength is 9.81 newtons per kilogram. Calculate the gravitational field strength close to the surface of Jupiter. So here I was using a simple expression, G is equal to capital GM over R squared. Consider it on the Earth's surface, consider it on Jupiter's surface. When I consider it on the Earth's surface, I'm actually considering the mass of the Earth. When I consider this expression on Jupiter's surface, I'm considering the mass of Jupiter, remember, with its radii. Come up with two equations and mathematically divide to find the answers. You don't need to substitute most of these constants. Like this constant may cancel out. Number 13, The moon and sun both contribute to the tides on the Earth's oceans. Which has a bigger pull on each kilogram of seawater, the sun or the moon? The moon and the sun both contribute to tides on the Earth's oceans. Which has a bigger pull on each kilogram of seawater? Is it the sun or the moon? I think this question is not very hard. When we talk about a bigger pull on each kilogram, that is the force per unit mass. Which one has a greater force per unit mass of seawater? Is it the sun or the moon? Justify your answer. You can even verify by calculating. You can find the pull per kilogram of seawater caused by the sun and the pull per kilogram of seawater caused by the moon, and then compare. But even without calculation, you can come up with a conclusion. Okay, number 14. Astrologers believe that the planets exert an influence on us, particularly at the moment of birth. They don't necessarily believe that this is an effect of gravity. Calculate the gravitational force on 4.0 kilogram baby caused by Mars when the planet is at its closest to the Earth at a distance of 100 million kilometers. Mars has a mass of this. So you want to find the force between a baby and Mars. Calculate the gravitational force on the same baby due to 50 kilogram mother at a distance of 0.4. So you calculate the force between the mother and the baby at a distance of 0.4. There is a point on the line joining the centers of the Earth and the Moon where their combined gravitational field strength is 0. Is this point closer to the Earth or to the Moon? Calculate how far it is from the center of the Earth. I will only attempt question 15. If this is the Earth and this is the Moon, let's say this is the line joining them. There is a point between the two. There is a point between the two where the combined gravitational field strength is 0. So if we consider a small test mass, of course, I know that the point is closer to the Moon because the Moon is less massive than the Earth. Therefore, its field strength is weaker than that of the Earth. So let's consider a small test mass m at that point. From the center of the Earth, it is at a distance which we are going to call x. And so from the center of the Earth is at a distance x. But we have been given in the list of constants above the distance between the Earth and the Moon. So it means this distance here will be the distance between the Earth and the Moon minus x. And I think the distance between the Earth and the Moon from the table given, the distance between the Moon and the Earth is 3.8 times 10 power 5 kilometers. So this will be 3.8 times 10 power 8 to change it to meters, then minus x. Or even if I don't change it from kilometers, I'll just say, okay, that is fine. So we want to find that point. I know it is closer to the Moon because the Moon is less massive than the Earth. Therefore, the gravitational field strength of the Moon is weaker than that of the Earth. So it spreads to a smaller distance compared to that of the Earth. So we can find this distance because is this point closer to the Earth or to the Moon? It is closer to the Moon because the Moon's gravitational field strength is weaker. Calculate how far it is from the center of the Earth. So we want to find x. So G at this point where the mass is caused by the Earth will be G caused by the Earth is going to be the mass of the Earth, which is 6.0 times 10 power 24 times the gravitational constant 6.6 7 times 10 power negative 11 divided by the distance from the Earth center, which is x squared. Then g caused by the moon is going to be 6. The mass of the moon is given as 6.4. We know the mass of the moon is not 6.4, 7.4. The mass of the moon is 7.4 times 10 power 22 times g is 6.67 times 10 power negative 11 divided by the distance from this point to the moon is going to be 3.8 times 10 power 8 minus x. This should be squared. Note that the gravitational force is always attractive. So the gravitational field is always attractive. The Earth attracts this mass towards itself. The moon attracts this mass towards itself. So the two values of g are in opposite direction. Remember, gravitational field strength is a vector quantity. So the resultant is obtained by subtracting. But they say there is a point where the combined gravitational field strength is 0. So these values of g are in the opposite directions for us to be able to get 0. So it means when I subtract them, I should get 0, which is as good as equating them. So I'll simply equate these two. So I'll say that 6.0 times 10 power 24 times 6.67 times 10 power negative 11 divided by x should be equal to 7.4 times 10 power 22, 6.67 times 10 power negative 11 divided by 3.8 times 10 power 8 minus x. So we are solving these two equations. I'm just going to pick my calculator for you can solve. Me, I know this has cancelled. I know I can reduce this power. By the way, this is squared. I can find a square root to both sides. So cross multiplying and finding the square root. Do I need to do this? Okay, I'll use the space up. I'm going to use the top space, cross multiplying. So when I cross multiply, I have 3.8 times 10 power 8 minus x. This is squared. Should be equal to, by the way, I'm cross multiplying. So this will be times 6.0 times 10 power 24 should be equal to x squared times, this will be 7.4 times 10 power 22. Okay, I want to divide and find the square root. I want to divide and find the square root so that I can collect like terms. So I'm going to take this one the other side. I'm dividing both sides, so I have 7.4 exponent 22 divided by 6.0 exponent 24. Then I find the square root to both sides. So it means everything, the square root is cancelling, so root of the answer. So I have that 3.8 times 10 power 8 minus x, square root has disappeared, is equal to this one, the square root has also disappeared. I divided this divided by that, find the square root to both sides. So this side I have 0.11 x. When I collect like terms, it means this goes the other side, so I'll say plus 1. So I have 1.1 x equaling to 3.8 times 10 power 8. So 3.8 exponent 8 divided by the answer. So this is giving me x as 3.4 times 10 power, this is 168 times 10 power 8 meters. So it is at a distance of about 3.4 times 10 power 8 meters. You can also try to go through that and see which answer you get. But the only technique is to know that when the gravitational field strength is 0, the value of G caused by the Earth is balancing with the value of G caused by the Moon. However, this is closer to the Moon because the Moon is less massive. Its gravitational field doesn't travel or doesn't spread over a larger area. Okay, so it is at a distance of 3.4 times 10 power 80 meters from the Earth. Okay, let's move to something different. Let's remind ourselves about mass and weight. In AS, we talked about mass and weight, and we said mass and weight are sometimes confused to be the same thing, but mass is a measure of a body's inertia to change its velocity, a measure of a body's resistance to change in motion, a measure of um, a body's resistance to change its position of rest or uniform motion. That is what we call inertia. There is a natural tendency of bodies to resist their state of either rest or uniform motion. That tendency is what we call inertia. We believe that a more massive object offers more resistance to change its state. Therefore, mass is considered to be a measure of that resistance. Mass is considered to be a measure of inertia. However, we know that the mass of a body remains constant unless the body is traveling at a speed close to that of light. If in practice we can't travel at a speed close to that of light, then it means the mass is going to always be constant. But in a gravitational field like the one we have been talking about, any mass placed in a gravitational field experiences a force. And we have already seen that the force experienced by that mass is given by the mass times the gravitational field strength, or the strength of the field in which the small test mass is placed. And that strength is what we call the weight. So the mass is a measure of the inertia of a body to change in velocity. Measure of the inertia of a body to changes in velocity is a measure of a body's resistance to change its motion. That is mass. A more massive object offers more resistance to change in its state of either rest or uniform motion. Number two, we have also said that in a gravitational field there is a force acting on the mass. This force equals to the mass and the gravitational field strength, that is m times g. And by the way, this is actually the weight from AS. We mentioned in AS that unlike mass, which is constant, the weight varies because weight depends on the value of gravitational field strength. And remember, the gravitational field strength of an object slightly varies. After all, we have seen that G at the poles is not the same as G at the equator. G is different because of the spinning of the Earth about its axis. Therefore, since G slightly varies as we move from one point to another point or from one part of the Earth to another point in space maybe, we can say that the gravitational force acting on an object reduces. Although the mass is constant, the weight is depending on the gravitational field strength. So if you are on the Earth's surface where G is approximately 9.81, your value of weight will not be the same when you go to the moon where G is 1.6 newtons per kilogram. So that one we saw in AS. So although mass is constant, weight depends on the gravitational field strength, which may not be constant from one point to another point. But of course, close to the Earth's surface, we said G is constant, so your weight will remain the same. Even when you weigh it on the bottom floor, it will be the same as when you weigh it on the top floor, even when you are 1,000 kilometers, meters above the Earth's surface. For your weight to be significantly different, you must move so many kilometers away from the Earth's surface. Okay, so weight is the pull of gravity on an object, the gravitational force on an object, the gravitational pull on an object, that will be the weight. So let's look at orbits. Let us look at orbits. So let's actually talk about orbits. What is an orbit? Of course, the word orbit has been common to us right from circular motion. We saw that the path followed by objects, um, the path followed by objects in a circle would be called orbits from circular motion. So an orbit is simply a path taken by an object around another object or around a common point. That is what we call an orbit. Normally, when we talk about orbits, we shall be referring to the path followed by objects in space, or the so-called celestial bodies that we mentioned in astrophysics and cosmology. So normally, why do we need to study orbits? It's because using these orbits, we can distinguish different objects. We distinguish different planets by basically relying on their orbits around the sun. But at this level, we shall not go into details of those orbits. However, we know if we have one mass moving around another mass, there is a force of attraction between the two masses, and we believe that the gravitational force of attraction between the two masses is the one responsible for keeping one object in orbit around another object. So let's consider an object orbiting or moving around the Earth. This could be a natural satellite such as the Moon. The Moon is a natural satellite orbiting around the Earth. Of course, the Earth is known to have only one moon. Some planets such as Saturn, some planets such as um, Uranus, they are known to have thousands of moons, so we call these natural satellites. So the Earth has only one natural satellite, the so-called moon or the moon. And of course, there are many artificial satellites which are orbiting around the Earth, together with the so-called spacecrafts or spaceships. There are a lot of debris and so on and so forth. All these are orbiting around the Earth's surface. But we know that now the gravitational pull of the Earth is the one which is keeping them in orbit around the Earth's surface. So the gravitational pull of the Earth is providing the centripetal force to keep these objects in orbit. So if we consider an object orbiting around the Earth, this object must be moving at a certain speed so that it remains in the same path around the Earth's surface or around the Earth. And this speed can easily be calculated. So let's consider an object such as a satellite of mass say m orbiting around the Earth. Let the radius of orbit, that is the distance between the satellite to the center of the Earth, be r. Let the speed with which the satellite is orbiting around the Earth be v, I will call the curvilinear speed. We know that the gravitational force Fg between the mass of the satellite and the Earth provides the centripetal force, I will call it Fc. So we need to establish the correct speed which is required to keep the object in its orbit or in a given orbit around the Earth. Which speed do we need to give this object so that it remains in its orbit around the Earth? So since the gravitational force provides the centripetal force, then I will start from this side and I say mass of the satellite times its speed squared over r is going to be equal to the gravitational constant times the mass of the Earth. I will call the mass of the Earth capital M times small m divided by r squared. That is according to Newton's law of gravitation. So I may establish the speed v squared is going to be equal to small m as cancelled, r as cancelled. This will be capital Gm over r, which means that the correct speed for such a satellite is given by this equation v squared equals to Gm over r. So depending on the height where the satellite should be, if we want to maintain that satellite at that height, then we should give it a correct speed which is equal to this, to capital G, that is gravitational constant, times the mass of the Earth creating the field divided by the distance from the center of the Earth to that height. It therefore follows from this equation that the closer the satellite is to the Earth's surface, the faster it must be moving. So if the satellite is very close to the Earth's surface, it will it will move very fast, it will have a higher speed. If it travels slower than this speed, then it will simply fall down. So if the satellite is close to the Earth's surface, then it must be traveling faster. It needs a greater speed to keep it in that orbit. If it travels slower than that speed, then it will just collapse towards the Earth's surface. Again, if it travels or if it is given a speed greater than the one it needs to remain in that orbit, then it will move to a higher orbit very quickly. If it travels too quickly, it will move out into a higher orbit. So it must be given a specific velocity, which is given by this expression to maintain it or to keep it in a certain orbit. This then calls for a thought experiment. A thought-provoking question. Here is my thought-provoking question. So I have a thought-provoking question. Suppose a satellite which is orbiting a few hundred kilometers above the Earth's surface experiences frictional drag from the Earth's atmosphere. Of course, there is air resistance, so the satellite is most likely going to experience what we are calling frictional drag or air resistance as it travels in its orbit around Earth. Of course, this air drag reduces its speed. The air frictional force wastes energy that would keep the satellite moving in its orbit at the same speed. That means the speed of the satellite is most likely going to slow down or it is going to reduce. So, what happens to the satellite if no precautions have been taken and the satellite is moving in its orbit around the Earth and air resistance come into play? What happens? This is the thought-provoking question. A satellite orbiting a few hundred kilometers above the Earth's surface will experience a slight frictional drag from the Earth's atmosphere. Draw diagrams to show how you would expect the satellite's orbit to change as a result. How can this problem be overcome if it is desired to keep a satellite at a particular height above the Earth's surface? So because it is losing energy, then it will not have the same speed to keep it in the same orbit as before. So this means it will have to fall towards the Earth's surface. What will be the what will be happening to this satellite as it moves in its orbit? Since it cannot remain in the same orbit because it loses speed due to air resistance, then if this was the original uh, orbit, let us assume this is the Earth, for example. Let this be the Earth. And the satellite starts from this point here. And air resistance comes into play. Let's assume that is moving in that direction, angular velocity is in that anti-clockwise direction. So because of air resistance, the satellite will fall off its orbit. So it cannot remain in the same orbit, therefore it will spiral as it falls off its orbit due to air resistance. But of course, it will be losing its kinetic energy, so it will spiral and collapse onto the Earth's surface. So the satellite will spiral towards the Earth. But precautions can be taken to prevent this so that we maintain a satellite at the same height. We can maintain the satellite at the same position and by taking several precautions. One, of course, we expect that as it moves in its orbit, it experiences air resistance. So there should be some way of always providing energy that overcomes air resistance without reducing its speed. So satellites can be launched with what we call thruster rockets. They can be launched with what we call thruster rockets. Of course, thrust comes from force. So let's say this is a satellite. I'm going to assume that this is a satellite. So on the satellite, we attach what we are calling thruster rockets. They could be many. So the satellite is designed with the thruster rockets. So as air resistance comes into play to compensate for the energy wasted in overcoming air resistance, it will fire off some of these thruster rockets. By Newton's third law, as it fires off some of these thruster rockets, there will be a resultant force forward which compensates for the work or the energy wasted in overcoming air resistance. So to maintain the speed and orbit, the satellite needs to fire small thruster rockets so that it maintains its speed and orbit. It needs to fire some thruster rockets in order to maintain its speed and orbit. So that is our thought-provoking question. Because if there is air resistance and there is no precaution taken, then the satellite will be falling towards the Earth's surface. It will fall off its orbit. So it means it will spiral towards the Earth's surface. But we can take precautions. Satellites can be designed with thruster rockets so that to maintain speed and orbit, the satellite fires off these small thruster rockets so that speed which is lost as a result of doing work against friction is always restored. Okay, since we are in orbits and we have been mentioning satellites, let's talk about artificial satellites. The moon is one of the natural satellites that orbit the Earth, but there are thousands and hundreds of artificial satellites which are monitoring the Earth. And these are actually launched in several orbits. These artificial satellites have a wide range or a variety of applications or uses. For example, many are used for making observations of the Earth's surface for commercial, environmental, meteorological, military purposes, to mention but a few. So satellites have a wide range of applications: communication, spying, meteorological, weather forecasting, business, and so on and so forth. So others are, by the way, used for astronomical observations, taking observations in space. So with the Earth as the reference, many astronomical observations can be taken using these satellites. We have seen TV communication for mobile communication. Many of these are also relying on satellites. So they are basically relying on artificial satellites. But satellites can be launched, or they are normally launched in two ways or in two orbits. Some satellites are launched so that they are always just above the equator, that they have what we call an elliptical orbit above or around the Earth's surface. They move in an ellipse around the Earth's surface. Then there are those, especially those which move from one pole to another pole. These ones move in a near circular orbit. So this figure is showing two typical orbits, an elliptical orbit and a circular orbit. A satellite, normally those moving from pole to pole, say south to north, back to south, and so on and so forth. These ones move closer to the Earth's surface, and they normally pass over the poles. These ones which pass over the poles, we are going, of course, to call these orbits or these satellites which normally move over the poles, we are going to call them later on polar satellites. Polar satellites. Note that the Earth flattens at the poles and bulges at the equator because the equatorial radius is greater than the polar radius. So a satellite moving from one pole to another pole and back will take a smaller time to make one revolution. For such reasons, satellites which move over the poles can make about 16 revolutions or 16 orbits in 24 hours or in one day. Such satellites, because they even move close to the Earth's surface, moving from one pole to another pole, they take a short period of time to make one revolution. So one satellite can make almost 16 orbits in just a single day. But satellites which move above the equator and are launched in elliptical orbits, many of these mostly take the same time as the rotation of the Earth to complete one revolution. In fact, for these satellites which are in elliptical orbit, as the Earth turns, they also turn with it. But for these satellites which are in a circular orbit, just moving from one pole to another pole, if a satellite X is viewing a country such as Rwanda here, as the Earth spins about its axis, remember it spins west to east. If Rwanda is now here, when the Earth is spinning from that direction about its north and south poles, it means this satellite cannot view this point of the Earth. But most of these elliptical satellites in elliptical orbits, if Rwanda is here and the satellite X is just watching over Rwanda, the satellite is rotating in the same direction as the spinning of the Earth. It means this satellite will always be above Rwanda. So, satellites can be launched in both circular orbits or elliptical orbits. You're going to notice that for circular orbits, the satellite is very close to the Earth's surface. So the area over which the signals are received and sent is very small. But a satellite in elliptical orbit, it has a wider view of the largest part of the Earth's surface. You notice that all this part, because it can be far away from the Earth, therefore it gives it a wider view of the Earth's surface compared to a satellite which is very close to the Earth's surface. So as we advance with the satellites, then we need not to forget the following. Number one, a satellite in a circular orbit close to the Earth's surface and passing over the poles could complete about 16 orbits in 24 hours, that is one day. And as the Earth turns below it, the satellite sees a different strip of the Earth's surface. So I said, for example, if Rwanda was here and this satellite was over it, because the Earth spins on its axis west to east, when Rwanda is now in this spot here, it means this satellite is not viewing, it will not be viewing anything above or anything happening in Rwanda at that moment. A satellite in elliptical orbit has a more distant view of the Earth. So the farther the satellite is away from the Earth's surface, the wider the area of view. I think this is practical in everyday life. When you move away from the object, I think you have a wider view of the object. Okay, so let's begin with the first and the most important satellites. This is the geostationary satellites. So satellites are going to be launched into two types of orbits, either in a circular orbit or in an elliptical orbit. Normally, those launched in elliptical orbits are called geostationary. They are called geostationary. Geo relating to the Earth and stationary relating to at rest. Why are they called geostationary? You might have wondered why, when you move through the city, you notice that all satellite dishes are facing in one direction. You might have asked yourself such a question: why is that our satellite dishes at home or even in the neighborhood must all be facing or are always facing in one particular direction? Geo relating to the Earth, stationary they appear as if they are at rest. In 1945, engineer Arthur Clarke proposed that let us have satellites launched in space. Let us have a series of communication satellites launched in space just above the equator in such a way that when an observer on the Earth's surface watches them, the observer gets an impression that these satellites are stationary. At that moment, Arthur Clarke looked a fool. Scientists were wondering, how can we have satellites in space that appear stationary to an observer on the Earth's surface? But today, as I speak, uh, the largest communication network is relying on geostationary satellites. So, a special type of orbit in which a satellite is positioned so that as it orbits the Earth, as it moves around the Earth, it appears to be stationary to an observer on the Earth's surface. This is what we call a geostationary satellite. The orbit in which it is launched or the orbit in which it moves is what we call a geostationary orbit. So Arthur Clarke suggested, let us have satellites, or let us have a series of communication satellites above the equator in what today we call it a Clarke belt. To him, he argued that these would allow telecommunication signals to leapfrog or to move from one part of the world to another part of the world easily. At that point, Arthur Clarke looked a fool. But today, as I speak, most of the satellites, a lot of satellites, a series of satellites are launched just above the equator. This line here is showing the equator. So most of these satellites are launched just above the equator. And communication can leapfrog from one satellite to another satellite to another satellite and so on and so forth, so that you can even watch a live match, you know. These are now the most common examples of or types of satellites. So to an observer on the Earth's surface, the satellite appears stationary. That's why it is given the name geostationary. Because the satellite appears stationary, your satellite dish does not need to be moved. It will remain facing in the same direction. Because even you, when you view the satellite, appears stationary. Therefore, it means relative to the satellite dish, it will still be stationary. Then why should we move the satellite dish? The question will be, why is the satellite stationary? Why does it appear stationary to an observer on the Earth's surface? So, there are a few reasons as to why it appears to be stationary for an observer on the Earth's surface. Number one, from Kepler's third law, the distance of a satellite in a geostationary orbit is related it can be obtained from Kepler's third law. Number one, we know that t squared is directly proportional to r cubed. We know that t squared is equal to a constant times r cubed. Of course, we know the constant. If the mass of the satellite is m and the mass of the Earth is capital M, we can tell this constant here because the gravitational force of the gravitational pull between the mass of the Earth and the satellite provides the centripetal force. So this constant T squared is going to be 4 pi squared over gm. Then this is times r cubed. Why does this satellite appear stationary to an observer on the Earth's surface? There are three important reasons, or four. Number one, this satellite is above the person, so it is above the equator. It is above the equator. So we say it is in equatorial orbit, just above the equator. It orbits above the equator. It orbits above the equator. Number two, it appears stationary because it is taking the same time to make one revolution around the Earth, just like the Earth itself about its axis. The Earth spins about its axis and it takes 1 day to make one revolution. That's why we have day and night. So because it spins, it takes 1 day to make one revolution. It takes 24 hours to make one revolution. It will also mean that this satellite is launched so that it takes the same time as the Earth itself to make one revolution. That's why you will not get an impression that it is moving, because it is going to take the same time like you who is standing on the Earth's surface to make one revolution. Therefore, the period of this satellite is 24 hours. The time taken for the satellite to make one revolution is 24 hours, just like the rotation of the Earth. Number three, it must be moving in the same direction as the rotation of the Earth, so that when you look at it, you don't get an impression that it is moving. If it were moving in the opposite direction, you would easily notice that it is moving, because it will be moving in the opposite direction to you, because for you, geographically, you move west to east according to geographers. The Earth spins about its axis west to east. So the satellite is also launched so that it spins it moves around the Earth west to east in the same direction as the rotation of the Earth. Going back to the second point, from circular motion, we saw that angular velocity is equal to pi over t. So if the period is the same as that of the Earth, it also means the angular velocity omega is the same as that of the Earth. So the angular velocity of rotation of the satellite is the same as that of the Earth. Of course, these three are enough because this implies this. So these are almost the same. So when somebody talks about a satellite which is in geostationary orbit, or a geostationary satellite, is referring to three major features. One, it is orbiting the Earth above the equator. Number two, it has a period of 24 hours. In other words, it takes 24 hours to make one revolution. Number three, it moves in the same direction as the rotation of the Earth, that is west to east. And if this is true, we can now try to establish how far do they launch such satellites? How far do scientists launch such satellites so that when you observe it, it appears as if it is stationary? Let's try to verify. So here I'm going to make r cubed the subject, or r the subject, as I substitute. So r cubed is going to be t squared. T is the period, which is 24 hours. So 24 hours, changing it to seconds, is I think it is 24 times 3,600. So the period is 86,400 squared times g, 6.67 times 10 power negative 11. M, I'm considering the Earth. The mass of the Earth is 6.0 times 10 power 24, divided by 4 pi squared. I'm pressing my calculator. So this is giving me 7.66 times 10 power 22. Of course, this is going to be meters cubed because this is r cubed. Then I find the cube root. I find the cube root of the answer so that I can find r. Remember, r is the distance from the satellite to the center of the Earth. So r is going to be equal to the cube root of this, which is 4.23 times 10 power 7 meters. That is r. So it means if a satellite is to be in a geostationary orbit, a satellite to occupy a geostationary orbit, it must be at a distance of around 4.23 times 10 power 7 meters from the center of the Earth. It must be at a point directly above the equator. It must be rotating west to east. What is this distance, by the way, from the Earth's surface? How far do we launch the satellites from the Earth's surface if the satellite is geostationary? So it means we need the height above the Earth's surface, which will be r minus the radius of the Earth. Remember, the radius of the Earth is 6.4 times 10 power 6. So I'm subtracting 4.23 exponent 7 minus 6.4 exponent 6. And I'm getting 3.6 times 10 power 7. So satellites which are in geostationary orbit are launched at a height of 3.6 times 10 power 7 meters from the Earth's surface. Points to note here. For a satellite in what we call a geostationary orbit, or we sometimes call it a Clark belt. But the word belt now comprises of a series of satellites. So it is a collection of satellites will form a belt. A collection of satellites in a geostationary orbit will form a Clark belt. But we are interested in three important features for such a satellite to appear stationary to an observer on the Earth's surface. Number one, it should be just above the equator. Number two, it should be having the same time as the period of it should be having the same period as the period of revolution of the Earth about its or the spinning of the Earth about its axis. It should be moving in the same direction as the rotation of the Earth, that is west to east. For such a satellite to observe on the Earth's surface, it will appear as if it is stationary. Okay, so let me first clear off this. So this is what I've been talking about. That for a satellite to occupy a geostationary orbit, it must be at a distance of 42,300 kilometers from the center of the Earth. This is what we have calculated as 4.23 times 10 power 7 in meters from the center of the Earth, and should be directly or orbiting directly above the equator. Since the radius of the Earth is about 6,400 kilometers, it implies that the orbital radius is about 6.6 times the radius of the Earth. You can verify that by calculation. So points to note. A few things we need to note here. Number one, a geostationary orbit, remember orbit is the path taken, is sometimes called a parking orbit. Geo, the Earth is the reference. Stationary, at rest. Of course, parking also relates to rest. A parking orbit can also be considered to be a geostationary orbit if the Earth is the reference point. But of course, if it is another planet, it will not be called geostationary. Maybe if it is Mars, it will be called metastationary or matostationary, something like that. We have several of these satellites orbiting around the Earth, over 300 satellites in such orbits. So this forms what we call a Clark belt. Several of them. Communication can leapfrog from one satellite to another satellite. communication can be linked between the satellites. That's what I'm meaning by leapfrog, you know. And these satellites are used for so many things. One of them is telecommunications. Telephone messages around the world could be relying on such geostationary satellites. Most TVs, satellite TVs, may be relying on geostationary satellites for communication. But normally what really happens? On the Earth, we have what we call a base station, which sends signals up to the satellite. What does the satellite do? The satellite will amplify them and broadcast them back to the ground. So information travels from the Earth to the satellite. Somewhere here in space, I have the satellite. So information is carried from the Earth to the satellite. In a unit called communication, which was scrapped off the syllabus, the frequency of the signal which goes to the satellite is called the uplink. The satellite does two important things. Number one is amplifying. The second one, which I'm not supposed to talk about, is changing the frequency at which the signal returns to the Earth. And the frequency at which the signal returns to the Earth is called the downlink. So you notice that if this is all the Earth, this is the Earth, a signal leaves the Earth to the satellite and back, you notice that it travels a distance twice. But remember, in a geostationary orbit, that distance is 3.6 times 10 power 7. Now, if it travels it twice, this will be almost times 2 because the signal goes and comes back. So since the signal travels the distance to the satellite and back, it means the signal may take a small time to arrive back to the Earth's surface, and that's what we are going to call time delay. This could be approximately 0.24 seconds or microseconds, 0.24 seconds as the time delay. Okay, so we are saying there is normally a base station here where we have the transmitter, that is the broadcasting point on the Earth's surface. And then now here I have the consumer, the person trying to receive the signal. The satellite receiver dishes are a familiar sight. You must have observed how in a neighborhood they all point towards the same point in the sky. That is our everyday experience. We see satellite dishes pointing in the same direction in a given area. The reason is very simple. These are because these satellites, or they are relying on satellites which are in geostationary orbit. The satellite dish can be fixed. One advantage of relying on communication using a geostationary satellite is that the satellite dish can be fixed. You don't need to begin changing the position of the satellite dish or to rotate it because there is a permanent link between the satellite on the Earth and the satellite dish in space. There is a permanent link between the satellite on Earth, the satellite dish on Earth and the satellite in space. So, since there is a permanent link, since the observer sees as if the satellite is stationary, then the satellite dish does not need to be moved. It can remain in one place. So one advantage of a geostationary orbit is that the dish can be fixed. Okay, we have also said, of course I've mentioned this, the advantage of geostationary is that the satellite dish can be fixed in one place. Satellites in any other orbits move across the sky so that a tracking system is necessary to communicate with them. I gave a simple illustration in the previous slide where we had a satellite moving from one pole to another pole, and the Earth is spinning west to east. At some point, a country such as Rwanda will not be just under that satellite, which is moving from one pole to another pole. So it means if we were to rely on one satellite moving from one pole to another pole, it means at some point Rwanda will not be under uh, surveillance, or Rwanda will not be seen by that particular satellite. But of course, there's a solution. If we are to rely on such satellites which need tracking, Of course, you can't track the satellite up to the poles, not at all. You can track it up to a certain point, of course. But we can have several satellites in such orbits. We can have as many satellites as possible in such orbits so that communication can easily be maintained with such satellites. One satellite can communicate with another, which also communicates with another, which also communicates with another, so that communication can be maintained. Let me give a simple example. Assuming this is the Earth and these are the pole, this is the axis of rotation. Of course, we know that the Earth will now be spinning from west to east, or it will be spinning from in that direction about its axis. So if we have satellites which are moving from one pole to another pole, we have satellites which are moving from one pole to another pole around the Earth's surface. So a satellite X should be linked with a satellite Y, which should be linked with a satellite Z, which should be linked with a satellite Z, and another satellite, and there will be other orbits also from pole to pole, other orbits, so that we have so many satellites moving from one pole to another pole. All these satellites should be linked with each other so that communication is maintained. So one, we have several satellites at or in orbits which are inclined to one another. These satellites should be linked so that at least at every point, at every moment in time, a country A will always be under surveillance by at least a certain satellite. When satellite X is here in this position here, another satellite has already arrived under A, so that communication is maintained. These two satellites must be linking up with each other so that communication which satellite X had already determined or was already receiving is not lost. Instead, it is just linked to the next satellite which is coming over point A. So it means if we are to rely on such satellites which move from one pole to another pole, we shall need many of them, and they should be linked in several orbits inclined slightly to each other. Of course, such a system is going to be very complex, expensive, and it will be too demanding for the domestic market. But for geostationary, we don't need to have so many satellites. After all, one particular satellite can maintain a permanent link with a certain point on the Earth's surface. For satellites moving from one pole to another pole, we need to have many of them in many orbits inclined to one another, so that one satellite can always communicate with a neighboring satellite and so on and so forth. At least there will always be a satellite above the Earth's surface, but it will not be the same satellite. Yet for geostationary, it will be the same satellite above that point of the Earth, because there is a permanent link. And lastly, geostationary satellites have a lifetime of almost 10 years, and for that reason, they need a fuel supply to maintain them in the correct. They will need a fuel supply to maintain them in the correct orbit and to keep them pointing correctly towards the Earth. So many times the satellites are always checked on to see if they are still in the same correct orbit, if they are still pointing towards the same points or the same part of the Earth, and so on and so forth. Of course, what what will cause them to move out of their orbit could be the frictional drag due to the Earth's atmosphere, or call it air resistance. Therefore, they need to be always fueled. Sometimes more thruster rockets can be added onto the satellites, because we have seen what the thruster rockets do. All this can be done so that their lifetime can be made longer. In summary, in summary, in summary, An object in a parking orbit or geostationary orbit has the following features, as we have said. Number one, we said the object is in equatorial orbit. It just orbits directly above the equator. Number two, the motion of the object is in the same direction as the rotation of the Earth. Note that the Earth rotates west to east geographically. So the object is also launched in such a way that it moves west to east. Number three, it has a period equal to that of the Earth's rotation about its axis. Therefore, that satellite should be moving around the Earth in a time of 24 hours, making one revolution in that time. And this leads to the fourth one, the angular velocity, this is omega from circular motion, is the same for this object as that of the Earth. After all, we now know that omega is 2 pi over t. If t is the same as that of the Earth, then omega should be the same as that of the Earth. Hence, for such a satellite, it will be probably a geostationary satellite, or sometimes it will be called a synchronous satellite, or it will be in what we call a geostationary orbit if it orbits the Earth with a period of 24 hours, the same direction as that of the rotation of the Earth, west to east, the same angular speed, and just above the equator. What is the consequence of all these three factors or four factors? For an observer on the Earth's surface, or from the viewpoint on Earth, the satellite appears to remain fixed in position above a point on the equator. And so the satellite dishes at home do not need to be moved, since the satellite does not need to be tracked. This gives it the name geostationary or parking orbit or parking satellite or geostationary satellite. Sometimes it is said to be synchronous. Two things are said to be synchronous, I think, if they are occurring or they are happening at the same time. So, for an observer on the Earth's surface, when you pick a powerful telescope to view a satellite in space which is in a geostationary orbit, it appears stationary. So if you have your satellite dish at home, you don't need to move it because there is a permanent link between that satellite dish and the point on the Earth's surface. I mean the point between that satellite dish and the satellite itself. Example. Not necessarily, we don't need an example here. Self-check, number 3. Self-check number 3. The moon orbits the Earth at an average distance of 338,000 kilometers from the center of the Earth. Calculate its orbital speed. Remember, the gravitational force provides the centripetal force. That one is a simple substitution. Number 2, the Earth is orbiting around the Sun. If the distance from the center to center of the bodies is this, remember I said this distance here is sometimes called the AU, astronomical unit, the average Sun to Earth distance. If the distance from the center to center of the bodies is this, and the period is 365 days and 5 hours, calculate the mass of the Sun. I think I will calculate this. So the centripetal force provides the gravitational force provides the centripetal force. It is now the Earth orbiting the Sun, so the mass of the Earth is small m. The Earth is even less massive than the Sun. For the Sun, I'll quote capital M. So the gravitational force is going to be capital G, capital M, small m over r squared is equal to mv squared over r. So small r has cancelled, small m has cancelled. So they are saying calculate the mass of the Sun. So capital G m over r is equal to, I'm removing v. V, remember, is omega r, which is 2 pi over t. V is omega, which is 2 pi over t. So I'm now substituting, this becomes 4 pi squared over t squared. By the way, there's an r here, so this becomes r cubed. Not r cubed, r squared. So when I substitute, I want m. So m is going to be 4 pi squared r cubed over t squared times g. Substituting. So this will be 4 pi squared times r, which is 1.51 times 10 power 11. But this is raised to power 3 divided by t. I'll begin with 6.67 times 10 power negative 11, that is g, times, now t, they gave us days plus hours. So it means I'll first change this from days, from days to hours, I add it to 5. Then the answer, I multiply it by the same 60 minutes to, 3,600 seconds, so that I change the answer to seconds. So I'll have 365 days times 24 to change it to hours plus 5. Now that is the total number of hours. Then times 3,600 to change this to seconds, and this should be squared because it is t squared. Pick your calculator. So when I pick my calculator, I'm getting m as being equal to 2.1 times 10 power 30 kilograms. You can also verify with your calculator. So the mass of the sun is approximately 2.1 times 10 power 30. Of course, we know the mass is approximately 2.0 times 10 power 30. So you can also verify using your own values. Using your own calculator. Okay, so you should attempt question number 1 as self-check number 3. Okay, do we have some applications of geostationary satellites? I think these are many, but I'll only concentrate on only 2. Applications and advantages of geostationary satellites. To start with applications, of course, telecommunication, mobile communication, TV communication, that is relying on satellite. Weather forecasting, mapping, and so on and so forth. That is relying on satellites, and so many others that you can talk about. Spying, there are so many. GPS, the global positioning system is entirely relying on these satellites. But it has one major advantage, and this is the antennas or the areas, or whatever you call them, or the satellite dishes can be fixed in position. That is an advantage. You don't need to always move the antenna at home because there is a permanent link between the satellite and the satellite dish on the Earth's surface. So since a geostationary satellite can have a permanent link with the transmitting ground station, the antenna or the area or the satellite dish does not need to be moved. Communication is maintained with any point on the Earth's surface that can receive that signal because there is a permanent link between the satellite and the satellite dish. So communication can always be maintained with any point on the Earth's surface that can receive the signal from the satellite. By the way, there could be a disadvantage. There is a disadvantage. Let me talk about just one disadvantage. There could be a disadvantage. And what is this disadvantage? Think of a situation when this is your satellite dish at home. This is the satellite dish on your house, and let's say the satellite is somewhere in space, far away from your house. So it is sending signals to the satellite dish. And if you are living near Kanombe and a giant plane comes in between the satellite and the satellite dish, here it means communication is going to be interrupted because communication lies on what we call line of sight. Communication can only occur provided there is no obstruction between the transmitter and the receiver, or between the satellite and the receiver. So communication can only occur if there is no obstruction between the receiver and the satellite, or between the transmitter and the satellite. If this is a giant plane just above, close to the house, just above the satellite dish, yes, above the satellite dish, then it means the signals from the satellite are being interrupted from reaching the satellite dish. So we say communication is limited to line of sight. Communication is limited to line of sight. In other words, the satellite dish should be seeing the satellite for communication to be not to be interrupted. That's what I mean by communication being limited to line of sight. That's one disadvantage of geostationary satellite. Because there is a permanent link between the satellite dish and the satellite, if something comes in between the satellite dish and the satellite, then the signal is lost. That's why I'm saying communication is limited to the line of sight. By the way, communication in polar regions is not going to be possible. So if you live near the poles, you can't rely on geostationary satellites, which are launched in equatorial orbits. So we are saying communication in polar regions, that is regions near the poles, is not possible. So you can't live near the poles and rely on communication using geostationary satellites, which are launched just above the equator. So that means another mode of communication could be necessary, or another type of satellites are going to be required. And this takes us to another type of satellites. Because communication is limited to line of sight, and communication in polar regions is not possible using geostationary satellites, then in the polar regions, another form of or another type of satellites could be required, and these are called the polar satellites. So we may need the polar satellites in the polar regions. We may need the polar satellites in the polar regions. The polar satellites, these ones are just moving from one pole to another pole, very close to the Earth's surface. So they move from one pole to another pole. Because the Earth flattens at the poles and the polar radius is smaller, it means they take a smaller time to move around the Earth. They take between 90 to 105 minutes. Most of these take between 90 to 105 minutes to make one revolution around the Earth. That's why we say they can make about 16 orbits in one day. Because the time for one revolution is very small. So this is what would make communication possible in the polar regions. But although these are good, although they make communication possible in polar regions, we have already seen the disadvantage of these. If we want communication to be possible with the polar satellites, we mentioned and said there should be many and inclined orbits. So if this is one orbit, we could be having another orbit somewhere like this. We could be having another orbit somewhere like this. So there should be many inclined orbits, many satellites in these inclined orbits, where all these satellites must be linked to one another so that communication can always be passed from one satellite to another satellite so that communication is maintained. And I said this is going to be a very complex system of satellite communication, and it will also make it very, very expensive. Very expensive. So communication relying on one satellite is not possible. That's one of the disadvantages. Communication using a polar satellite, a single polar satellite, is not possible. I can talk about several advantages when I'm talking about these satellites, but I will talk about just a disadvantage. So communication using one satellite is not possible. That is the major disadvantage of polar satellites. If we have only one satellite, satellite X, it means when satellite X comes to the North Pole, people at the South Pole have no communication. So if we want to maintain communication at the South Pole, then we should have several satellites in this orbit which are linked to each other so that at least at every point, at every moment in time, there is a satellite just above the South Pole. These satellites must be communicating with each other so that communication is continuously achieved with these satellites. These are normally, because they take a short time to move around the Earth, they can be used to see changes in the weather, quick changes in the weather. It makes one revolution. After 90 minutes, the weather has changed. It will be observed very fast. Then they can be used for world mapping. When they talk about world mapping, you also think about the GPS, that is the global positioning system. Espionage and spying normally relies on polar satellites because of the short time they take to make one revolution. So they give information from the same point many times in a single day, you know. So those are some of um, the polar some of the applications of polar satellites. Examples. Let's do a few examples. Let's do one or two examples. Example number one. For a geostationary satellite, calculate the height above the Earth's surface, the speed in orbit. I think we have already calculated the height, but for those who have been absent-minded, we can still calculate this. For a geostationary satellite, calculate the height above the Earth's surface and the speed. So we know from Kepler's third law, we have already seen that the gravitational force provides the centripetal force. Using that, gravitational force provides the centripetal force. We know that now from this we shall have Gmm over r squared is equal to mv squared over r. And when we substitute m as cancelled. Remember, v is equal to 2 pi over t times r. You square and make t the subject. I don't want to repeat that algebra. So we shall have that r cubed is equal to g m divided by 4 pi squared times t squared. I've substituted this into that and I made r cubed the subject because I want the height above the surface. And remember, the height h will be the radius of orbit minus the radius of the Earth. So we substituted in one of the examples 6.67 times 10 power negative 11 multiplied by the mass of the Earth, which is 5.98 times 10 power 24 multiplied by period. Since it is geostationary, the time is 24 hours. So 24 hours the same as 86,400 squared. Then divide this by 4 pi squared. I press my calculator once again. So I am getting 4.23 times 10 powers. I found the cube root. So this is 7.54 times 10 power 22 because it's r cubed. This is meters cubed. So r is the square root. The cube root, which is 4.23 times 10 power 7 in meters. So that is r, but we want h, the distance above the Earth's surface. So h is going to be 4.23 times 10 power 7 minus the radius of the Earth. The radius of the Earth has been given as 6.38 times 10 times 10 power 6. So this is giving me 3.59 times 10 power 7 in meters. Then the speed in orbit, that is v. So this was part A. Part B, I think the speed in orbit is very easy. I can even use v is equal to 2 pi over t times r, 2 pi times the radius of orbit, which I've got as this one, 4.23 times 10 power 7, divided by the period, since it takes 24 hours, that is 86,400. So it is 86,400. So I can press my calculator. Remember, this is 2 pi. So this is approximately 3070 meters per second. So that will be the speed. The last example I will do for today. A satellite is launched in a circular orbit about the equator at a height is 3.6 times 10 power 4 kilometers above the surface of the Earth. Given that the mass of the Earth is this, and its radius is this, find the radius of orbit. So it is launched at this height. The height is 3.6 times 10 power 4 kilometers. The radius of the Earth is this. So it means the radius of orbit, r, is simply going to be the height, the radius of the Earth, plus h. Just add these two. 400 plus 360. So this is giving me 42,400 kilometers as the radius of orbit. Then the speed with which the satellite is launched. So remember, the gravitational force provides the centripetal force. So capital G, capital M over r squared is equal to the centripetal force mv squared over r. So this cancels. So the speed v is going to be the square root of capital Gm over R. We substitute, this will be square root of 6.67 times 10 power negative 11, then times M. M is given as 5.98 times 10 power 24, divided by the radius of orbit, which is 42,400. 42,400, but this is in meters. You add those two zeros. So press the calculator. So this is 3067, approximately 370 meters per second. Then the period, I think the period is very easy. The period is very easy. If you want, you can, by the way, use the speed. If you want, you can use the speed. Since the speed is equal to pi over t, that is omega times r, which is now 30/70. So it means the period will simply be 30, sorry, not 30. I'm making the period the subject, so this will be 2 pi times the radius of orbit, which is 42,400. I added 3 zeros to change it to meters, divided by 30/70. So this is equal to 8.68 times 10 power 4. This is in seconds. I can change it to hours. I will divide this by 3,600. This is giving me 24.1, or approximately 24 hours. So that is automatically 1 day. That is taking 1 day. So that will be the period of that satellite. So it is in geostationary orbit. It takes the same time as the period of rotation of the Earth. It must be above, because they say it is above the equator. You see, it is launched at this height, so it is geostationary. Okay, so I hope that is home and dry. We qualify for self-check number 4. Self-check number 4. Show that Newton's law of gravitation is consistent with Kepler's third law. In other words, you just derive t squared directly proportional to r cubed. Show that the mass of the sun is given by this. This equation relates to the first one. Remember, the gravitational force always provides the centripetal force. Okay. Two 2.5 kilogram masses are placed with their centers 10 centimeters apart. Calculate the size of the gravitational attraction force between them. That one is easy. You just need the force, Newton's law of gravitation. The mass of the moon is 7.4 times 10 power 22 kilograms. Its radius is 1.7 times 10 power 6 meters. Using the value of G from question 3, of course, capital G is 6.67 times 10 power negative 11 newtons meters squared per kilogram squared. Calculate the free fall acceleration at the moon's surface. So you are finding small g. You're finding small g at the moon's surface. You verify if that is correct. Number 5. The mass of the Earth, ME, describes a circular orbit radius RSE about the Sun, of mass ms, and radius rs. Angular velocity is that due to the gravitational attraction, given that RSE over RS is equal to 200, calculate the density of the sun. I think I should work out this one. So the mass of the Earth describes a circular orbit of radius that about the sun. So the distance between the center of the Earth to the center of the sun is that. So the gravitational force between the mass of the Earth and the sun provides the centripetal force on the Earth. So I will say that capital G, mass of the sun, mass of the Earth, divided by the distance between the two is given as R/S/E, but this is squared, should be equal to the mass of the Earth times V squared over R/S/E. So this one cancels with that square, ME has cancelled. Remember that V is equal to omega, the speed is equal to omega times the radius of orbit, which will be RSE. The radius of orbit is RSE. Omega has been given. Okay. And also remember density of the sun, because they want us to calculate the density of the sun. The mass of the sun is equal to the density of the sun times the volume of the sun. But the sun, assuming it is spherical, this will be density times 4 over 3 pi. Now this time it will not be RS, it will be instead RS, because we are looking at the sun. So radius of the sun cubed. Mathematics is sweet and simple. Okay, so I'm now going to substitute. I'm going to substitute all this equation and this constant quantity here, and I make the density the subject. So G times density times 4 over 3 pi radius of the sun cubed divided by RSE should be equal to, this side I have this squared, so this should be omega squared RSE squared. Okay, so I want, whenever I see RSE over RS, I know it is 200. So I'm going to make a density the subject. So density is going to be equal to, this side I have 3. This 3 goes the other side. Omega squared times RSE, but this is going to be cubed. Divided by, here I will divide by RS cubed. And I will also divide by G of 4 pi times G. 4 pi times G divided by RS cubed. So that's what I have as the density. Whenever I see RSE over RS, I know it is 200. So it means the density of the sun is going to be 3 times the angular velocity, which is 2.0 times 10 power negative 7. Then divide by 4 pi times G is 6.67 times 10 power negative 11 times, this is RSE over RS but cubed, so this becomes 200 cubed. I pick my calculator, 3 times 2 exponent negative 7 divided by 4 pi times 6.67 exponent negative 11, then times 200 times 200 power 3. Oh, by the way, omega was squared. I have to press this again. 2 exponent negative 7 squared times 3 divided by 4 pi times 6.67 exponent negative 11 times 200 cubed. So this is 1145.3 kilograms per meters cubed. You can check. My calculation could be wrong, but you can check. I can check it again. 2 exponent negative 7 times I think that is wrong. Times 3 divided by 4 pi times 6.67 exponent negative 11 times 200 cubed. Yeah, you can verify I'm getting that. So self-check, number 5 is done. We go to number 6. A 1,000 kilogram satellite is launched in a parking orbit above the Earth's surface. Calculate the height of the satellite above the Earth's surface. That is easy. Calculate the ratio of the mass of the Earth to that of the Sun, given that the Moon moves around the Earth in a circular orbit of radius this, with a period of that, and the orbit radius of the Earth around the Sun is this, and its period is that. So we want to calculate the ratio of the mass of the Earth to that of the Sun. Then the distance of Jupiter from the Sun is 5.2 times the distance of the Earth from the Sun. Assuming that both orbits are circular, find the time Jupiter takes to complete its orbit. If the Earth takes 1 year, I think I can also try to give a hint on this. So since Jupiter and Earth both are orbiting the same center, then the equation t squared is equal to a constant times r cubed applies directly. So if the distance of the Earth from the Sun is d, that one of Jupiter from the Sun will be 5.2 times d. So period of Jupiter squared divided by period of the Earth squared should be equal to a constant k times the distance of Jupiter from the Earth from the Sun will be 5.2 times d cubed. If the distance of the Earth from the Sun is d cubed. So you notice that d has cancelled. And note that the period of the Earth is 1 year. So it means the period of Jupiter squared is going to be 1 year. That is the period of the Earth squared times 5.2 raised to power 3 because d cubed cancels. Note that this is 1 year. So t Jupiter is equal to 1 year squared times 5.2 cubed under the square root. So I just find the square root of 5.2 cubed, which is 11.9 years, because I didn't change time from years to any other unit. When a space shuttle is in orbit at a mean height of this above the surface of the Earth, it requires 91 minutes to complete one orbit. Find the value of the mass of the Earth. That's number 9. Next, the radius of the Moon's orbit is this, and its period is 27.4 days. Use Kepler's law to calculate the period of orbit of a satellite orbiting the Earth just above the surface. When they say just above, It means the radius of orbit of the satellite is approximately the same as the radius of the Earth. Because if the satellite is, say, 100 meters above the Earth's surface, it means the radius of orbit will be the radius of the Earth plus 100 meters, which is approximately the same as the radius of the Earth. So when they say just above the Earth's surface, it means the radius of orbit is approximately the same as the radius of the Earth. Then number 11, for any future mission to Mars, it would be desirable to set up a system of 3 or 4 geostationary or mattostationary satellites. Now we are considering Mars, so the correct way of calling it would be mattostationary satellites around Mars to allow communication between the planet and Earth. Calculate the radius of a suitable orbit around Mars. Mars has this mass and its period is this. So we want the radius of a suitable orbit around Mars. Calculate the radius of a suitable orbit around Mars. For any future mission to Mars, it would be desirable to set up a system of 3 or 4 mattostationary satellites around Mars. So we want them to appear stationary to unobserved on Mars. So they should have the same period as the rotation of Mars about its axis. They should be above the equator of Mars if it is there, and they should be rotating the same direction as the rotation of Mars. And lastly, although some international telephone signals are sent via telecommunications satellites in geostationary orbits, most are sent along cables. Most of these are sent along cables. We know optic fibers on the Earth's surface. This reduces the time delay between sending and receiving the signal. Estimate this time delay for communication via a satellite and explain why it is less significant when cables are used. What do we mean by the time delay here? For communication using a satellite, what do we mean by the time delay? The signal, remember, will travel from the Earth to the satellite and come back. The signal travels from the Earth to the satellite and then comes back. The signal travels from the Earth to the satellite and comes back. So the time to travel that distance will be twice the distance between the satellite and the Earth over the speed of light, because time is distance over speed. So the distance, note that for satellites in geostationary orbits, they are launched to a vertical distance of 4.23 times 10 power 7. That means above the height of the sun, because they are launched from the surface of the Earth. This distance is going to be 2 times 3.6 times 10 power 7. We have already seen this. You can verify this in calculation, of course. Divide by 3 times 10 power 8. So this will be 2 times 3.6 exponent 7 divided by 3.0 exponent 8. This gives us a time of about 0.24. So the signal will take about 0.24 to reach a receiver on the Earth's surface, because it will travel a distance of 3.6 to the satellite and then 3.6 back to the Earth. 3.6 times 10 power 7. You can verify that since it is geostationary. You need to find the radius of orbit, then obtain the height of a geostationary satellite above the Earth's surface. But remember, the signal travels the distance from the surface to the satellite twice. Then dividing by the speed of light, because communication is relying on microwaves, then the time is twice. Then explain why it is less significant when cables are used. Why is it that the time delay is smaller when cables are used? That one is obvious. Cables run around the Earth's surface. The circumference of the Earth is smaller than the distance from the surface of the Earth to a geostationary satellite and back. You can try to find the circumference of the Earth, considering the radius of the Earth as this, You can try to find the circumference of the Earth. Of course, the circumference of the Earth is 2 pi r, I think. You can try to find this circumference. This is 2 pi times 6.4 times 10 power 6. So this is 6.4 6.4 exponent 6 times 2 pi. So this is approximately 4.02 times 10 power 7. And this distance is smaller than this distance here. So it means even if the signal moves around the Earth's surface, the distance covered, remember the signal is all using light, because using cables, the signal travels by optic fibers, which are relying on light. So the time delay will now be this distance divided by this speed. Because the distance around the Earth is smaller than the distance from the Earth's surface to the satellite and back, the time delay using cables is smaller than the time delay using satellites or relying on satellites. I think I've explained that. Because the distance around the Earth is smaller than the distance from the Earth's surface to the satellite and coming back, then the time delay using cables will be smaller than the time delay relying on satellites. Okay, I want to stop here for today, and I hope you have a very beautiful evening. See you.